Yeah, welcome back to the channel. Today we cover pedigree diagrams. Now, what is a pedigree diagram? A pedigree diagram is a diagram which simply shows the inheritance of different characteristics and disorders in a family. So with a pedigree diagram, we're going to try to trace the origin of certain characteristics and also disorders. The cases may differ, but the approach is the same, right? Now, the inheritance that we're going to trace, it may be autosomal, sex-linked, or it may even include blood groups. It doesn't really matter. Again, the approach is the same, right? We're going to try different examples to show this, right? And then it says that it is most important to be able to identify the genotypes and phenotypes of each and every individual in the pedigree diagrams. And as a matter of fact, this is going to be the main focus. The main focus in this video is to be able to tell the genotype and the phenotypes of each and every individual in a pedigree diagram, right? Let's get started. Now, before we approach this question, there are some things that we need to understand first. First of all, it is the key that is provided in each and every pedigree diagram. Now, it is the norm that the squares represent males and the circles represent females, right? So it is very important to look at the key before you try to answer questions that are involving pedigree diagrams. Again, the squares represent the males and the circles represent the females. Now, this is a typical example of what we call a pedigree diagram. Now, how do we read this? Now, when we try to look at individual number 1 and individual number 2 respectively, this is a female, that is number 1, and we've got a male at number 2. Now, female number 1 and male number 2 are linked together by this horizontal line. Now, a horizontal line like this between a female and a male simply tells us that these are parents. These are people who are maybe married, for example. So 1 and 2 are parents, and we know they are parents simply because they are connected by this horizontal line, right? Now, a vertical line arising from this horizontal line tells us that individual 1 and individual 2 had offspring. They had children, right? Now, how many children exactly did individual 1 and individual 2 have? They had 3 children. And the children of individual 1 and individual 2 are represented by individuals 4, 5, and 6, right? Now, a person may ask, why is individual number 3 not being counted as being an offspring of individual 1 and individual 2? If we look closely at individual 3 is connected to individual 4 by means of this horizontal cross. But remember, we said that these horizontal cross simply represent that individual 3 and individual 4 are parents. This is a couple. These are people that are married. So individual 3 is not an offspring of individual 1 and individual 2. Individual 3 is dating or has a relationship with individual number 4, who is the child of individual 1 and individual 2. Now, seeing that individual 3 and individual 4 had a baby and they only had one baby. Again, we know that individual 7 is an offspring of individual 3 and individual 4 simply because the line leading to individual number 7 is a vertical line that is joining the horizontal line that joins individual 3 and also individual number 4, right? So individual 3 and 4 are connected by this horizontal line, so they are parents. And then the vertical line arising from this horizontal line shows that number 7 is an offspring. It is a child of individual 3 and individual number 4. So that is basically how we read these pedigree diagrams, right? So let's wrap this. Let's wrap this and let's get to it. Right. Now, the most important thing to do here is being able to identify the genotype and phenotype of each and every individual in this pedigree diagram. Now, the easiest part to identify between the genotypes and the phenotypes will be the phenotypes, and that is simply because we are already given the phenotypes. The phenotypes are given by the key here that is provided. So we know that each and every single time we look at a white box in this pedigree diagram, it will be representing a male without Tay-sex. But when we look at a white circle, it will represent a female without Tay-sex. But looking at a black box, it will tell us that that is a male with Tay-sex, and a black circle, it is a female with Tay-sex. So these will be our phenotypes, right? Now let's try to come up with the genotype for each and every individual in this pedigree diagram. Now it is important to note we may use the genotype of the offspring to determine the phenotype of the parents. And this simply goes simply because of the idea that the genotype of each and every individual will be represented by two alleles. Why is it represented by two alleles? One allele will come from the paternal origin and the other allele will come from the maternal origin, right? So we're going to use that idea that each and every genotype has got two alleles, one allele from the paternal origin, the other allele from the maternal origin, right? So before we try to come up with the genotypes, let's read the instructions. The instructions state, the diagram below shows the inheritance of Tay-sex, a rare disease which leads to the destruction of neurons. It is inherited as an autosomal disorder controlled by two alleles. The alleles in question are capital letter T and small letter t. Now, there's something to note here. They did not tell us which allele causes Tay-sex. Rather, they simply gave us the alleles responsible as capital letter T and small letter t. But if I come back here to my key, I know that a black circle and a black box will represent a person who has Tay-sex, right? So for example, let's try to look at individual 5. Individual 5 is an offspring of individual 1 and individual 2. But individual 5 is a female with Tay-sex. But this individual with Tay-sex is an offspring of individual 1 and individual 2 without Tay-sex. It tells me that individual 1 and individual 2 have to be heterozygous. Therefore, if they are heterozygous, they were able to each distribute an allele that causes Tay-sex to individual number 5. Hence, this offspring is going to have Tay-sex. But since individual 1 and individual 2 do not have Tay-sex, it tells me that individual 1 and individual 2 must be carriers. It tells me they must be homozygous. They must be heterozygous, not homozygous. They must be heterozygous simply because individual 1 and individual 2 do not have Tay-sex, but they were able to give birth to an offspring with Tay-sex. It tells me that this Tay-sex has to be caused by the recessive allele small letter t. Again, simply because parent 1 and parent 2 do not have Tay-sex, but they were able to give birth to offspring number 5 with Tay-sex. So individual 1 and individual 2 are carriers. They are heterozygous. Hence, they were able to distribute a recessive allele each to individual number 5. So the very first and the most simplest of the genotypes to identify is the genotype of individual number 5, and it is going to be small letter t, small letter t. Now again, this small letter t, one of these small letter t has to come from parent number 1, and the other small letter t has to come from parent number 2. So I know that individual 1 and individual 2 have a small letter t in their genotype. But since they are not affected by Tay-sex, it tells me that they must be heterozygous. So it is capital letter T, small letter t. The same will apply for the male parent, which is going to be capital letter T, small letter t. Right. Now, let's talk about individual number 6. Now, individual number 6 is a male without Tay-sex, right? And remember, the genotype of each and every individual is represented by two alleles. One allele coming from the paternal origin, one allele from the maternal origin. So since offspring number 6 does not have any children, he may have two possible genotypes. And that is simply because it is possible for individual number 6 to be a male without Tay-sex if he received capital letter T from the mother and capital letter T from the father. So he will still be a male without Tay-sex. Or if he received capital letter T from one of the parents and small letter t from one of the parents, he is still going to be a male without Tay-Sachs. So for individual number 6, there are two possible genotypes: capital letter T, or capital letter T, small letter t. There is no way for us to be sure which genotype is correct, since individual number 6 do not have offspring of his own. If he had offspring of his own, we would be able to trace the genotype and try to be more specific, but since it doesn't, we'll resort to a possibility of these two, right? But now let's look at individual number 4. For individual number 4 was married to individual number 3, and they were able to have a child who is individual number 7, right? But we know that Tay-Sachs is caused by the recessive allele small letter t here. And in order for the recessive allele to determine the phenotype, the genotype must be made of the two recessive alleles, which means that the genotype of individual number 7 has to be small letter t, small letter t. But this small letter t, one has to come from each parent, telling me that parent number 3 has a small letter t. The same also apply for parent number 4. But since they are unaffected by Tay-Sachs, it tells me that individual 3 and individual 4 both have to be heterozygous. Hence, they were able to give individual number 7 small letter t on this side and small letter t on that side. They cannot be homozygous, because if one of these parents was homozygous dominant, hence they had the genotype capital letter T, they would not be able to have an offspring with Tay-Sachs, because the dominant allele in that case would always determine the phenotype. So it only makes sense for individual 3 and individual 4 to both be heterozygous. So they are unaffected, they are normal, right? So that is all the genotypes of these individuals identified. Let's do another example. So this example focuses on moyamoya. Moyamoya is a disorder caused by a dominant allele, capital letter R, okay? This disorder damages the arteries supplying blood to the brain. The pedigree diagram below shows the inheritance of moyamoya in a family. Before we try the pedigree diagram in itself, let's look at the key: a white box, unaffected male; black box, affected male; white circle, unaffected female; black circle, affected female, right? Now, the instructions here are very simple. Moyamoya is caused by a dominant allele, which is capital letter R. And the person who is affected by moyamoya here would be black. So a black box and a black circle. Those are people that are affected by moyamoya. Now let's try to come up with the genotypes, right? Let's look at individual number E, for example. Individual number E is a male with moyamoya. And if individual E has moyamoya, it tells me that individual E must have a dominant allele. So this person has to have capital letter R, right? If individual number E has capital letter R, what is the other allele making up this person's genotype? And we can simply do this by looking at the children. We could have started with any of the individuals and the result will be the same. Just that I chose to start with number E, right? Number E has moyamoya, so he must have capital letter R because it is caused by a dominant allele capital letter R. So number E married number F, but number E and number F were able to produce an offspring without moyamoya, that is individual H here. But since individual number H does not have moyamoya, it tells me that the genotype of individual number H has to be small letter r. Because again, remember, moyamoya is caused by a dominant allele capital letter R. So if you do not have moyamoya, it tells me that you must have two recessive alleles. Hence, you must be homozygous recessive. So individual number H, the genotype can only be small letter r for this person to not have moyamoya, right? But since individual number H has got small letter r, it tells me that one small letter r was from the paternal origin and the other small letter r was from the maternal origin. So individual number E has to be heterozygous for moyamoya. So it must be capital letter R and small letter r. But when I look at individual number F does not have moya moya. Again, moya moya is caused by a dominant allele. So if you are without moya moya, you can only be homozygous recessive. Therefore, the genotype for individual number F has to be small letter r, right? Now let's come to individual I and J. And the genotypes for individual I and J are very simple to tell, simply because individual I has moya moya. So she must have a capital letter R. And this capital letter R can only come from individual number E, who is the paternal origin. But since individual number F is homozygous recessive, individual number I can only be heterozygous for moya moya. Capital letter R coming from father E and small letter r coming from mother F. The same will also apply for J. It is the same story as in number I. So the genotype is going to be that one, right? Now let's come to individual number B. Individual number B, that is a female without moya moya. So since this is a female without moya moya, the genotype is small letter r. But let's come to individual A now. Individual A, is this person homozygous dominant or is this person heterozygous? Individual number A can only be heterozygous for moya moya. Why do we say that? Individual A and individual B were able to give birth to individual number D. Now, individual number D is a female that is not affected by moya moya. So since individual number D is not affected by moya moya, then the genotype of individual number D can only be small letter r. Again, since this is the genotype of individual number D, she must have received one recessive allele from the paternal origin and one recessive allele from the maternal origin. Therefore, the genotype of individual number A, since this is a male with moya moya, he must have capital letter R. But he was able to give birth to a female child without moya moya. And since she is without moya moya, her genotype is small letter r. Therefore, the genotype of the parent number A has to be capital letter R, small letter r. He must be able to give this child this small letter r. So individual number A has to be heterozygous. Let's look at individual number C. Individual number C and individual number D were able to give birth to baby number G. Baby number G is a female without moya moya. Therefore, the genotype is also small letter r. But individual number C has moya moya. Therefore, it must have capital letter R. But since this child is without moya moya and has the genotype small letter r, one small letter r must come from the paternal origin, one small letter r from the maternal origin. Therefore, individual R can only be heterozygous for moya moya. And that is all the genotypes of the individual in this family, right? Let's continue. Now let's look at this pedigree diagram. It says that severe combined immune deficiency syndrome, SCID, is a disorder affecting the immune system. It is caused by a sex-linked recessive allele. So this is a sex-linked genetic disorder. Now, it is very important to note that when we are writing the genotypes that include sex-linked genetic disorders, we must also include the gonosomes. It forces us to use gonosomes, right? Now, it says that the diagram below shows the inheritance of the disorder in a family. It is not known if individual 1 has the disorder or not. We will be able to find it. So, it is also important we know that this this severe combined immune deficiency, SCID, is caused by this recessive allele, x to the exponent of small letter d. Now, let's try to find the genotype of each and every individual in this family. Now, what is very simple to do with cases that involve sex-linked genetic disorders is that we know that the gonosomes of females have to be XX. And the gonosomes of each and every male has to be XY. What is left there is the allele responsible for the disorder, right? Now, let's look at individual number 4. Now, individual number 4 is a female, right? But this is a female with SCID, according to this key. So this female has got SCID. But we know that the gonosomes of females have to be XX. right? And we know that SCID is caused by the allele X to the exponent of small letter d. Therefore, since individual number 4 has SCID, it tells me that she must be homozygous for SCID. She must have this recessive allele in all her X chromosomes. So her genotype can only be this one. This is the only possible genotype for this female, right? But let's go back to individual number 2 now. Individual number 2 is the mother of individual number 4. And since she is female, she must have XX chromosomes. But individual number 2 is without SCID, but she was able to give birth to an offspring, which is number 4, who has SCID. Therefore, individual number 2 has to be heterozygous. She is a carrier of SCID. So a genotype can only be X capital letter D, X small letter d. This is the small letter d that she was able to pass on to individual number 4, right? Now let's look at individual number 1. Individual number 1 has to be the father because this is the circle representing the mother. Therefore, individual number 1 has to be the father. So the genotype of the father has to be XY. But to tell if this individual has SCID or not, we look at individual number 4, who is the child of individual number 1. So individual number 1 has to have SCID. Why? Individual number 4 has 2 X chromosomes, both with the recessive allele for SCID. Therefore, one gonozome has to come from the maternal origin and the other gonozome must come from the paternal origin. Therefore, this father suffers from SCID. He must be a black box. If we were to draw the box here, it must be a black box, right? So he has to suffer from SCID. Again, the female child here has got 2 X chromosomes. One gonozome is coming from the father and the other gonozome is coming from the mother. They are both carrying the recessive allele for SCID. Therefore, the father has to have SCID since he only has the 1 X chromosome, right? Now, let's look at individual number 3. Now, with individual number 3, it is possible for individual number 3 to have 2 possible genotypes. But due to the fact that individual number 3 married this male and they had 2 children, both of whom are without SCID, it may be possible that the genotype of individual number 3 has to include the capital letter D. And this capital letter D, we know that it is coming from the maternal origin. It is coming from number 2 there. But since the father suffers from SCID, individual number 3 can only be heterozygous. She is a carrier because, again, she receives 1 gonozome from the maternal origin and 1 gonozome from the paternal origin. So the dominant allele has to come from the maternal origin. Since she is female, she received the X chromosome from the father. But the X chromosome from the father has the recessive allele. Hence, the genotype of individual number 3 has to be X to the exponent of capital letter D, X to the exponent of small letter d. The small letter d comes from the paternal, the capital letter D from the maternal, right? Now, the partner that she married, which is this box here, this is a male without SCID. Therefore, his genotype can only be X capital letter D, Y. And then let's come to this child. She is without a number, but this one. So she must receive an X chromosome from the father and an X chromosome from the mother. So she must have 2 possible genotypes. So she can either be homozygous dominant, she can receive the capital letter D from the father and the capital letter D from the mother, or she may receive the capital letter D from the father and the small letter d from the mother. She will still be unaffected. She will still be without SCID. Let's come to the male. The male receives the Y chromosomes from the father because the Y chromosome is only present in the father. Therefore, his genotype is XY. But since he is without SCID, it tells me that he has the capital letter D on that X. And this X capital letter D can only come from the maternal origin. Since again, in males, the Y chromosome is inherited from the paternal origin. So the X to the exponent of capital letter D can only come from individual number 3, who is the mother, right? Now let's come to the partner of individual number 4. The partner of individual number 4 is a male without SCID. Since this male is without SCID, his chromosomes again are XY, and the allele has to be capital letter D. But when we come to individual number 5 is a male, therefore his chromosomes have to be XY. Again, the Y has to be inherited from the paternal origin since this is a male, and the X has to carry the recessive allele for SCID. This is simply because individual number 4 is homozygous recessive, is a female with SCID. So this son will always receive the X small letter D from the mother. As a matter of fact, each and every son born from the marriage of number 4 and their partner will always have SCID, simply because the X chromosome will only come from the maternal origin, and all the X chromosomes in the maternal origin have the recessive allele for SCID. So each and every son born from this combination will always have SCID. Now let's come to the female. The female has the chromosomes XX, one X from the maternal, one X from the paternal. But the X of the father has the allele capital letter D, so she is without. But from the maternal origin, she will only receive an X with the small letter D. So the only possible genotype for this individual is to be X to the exponent of capital letter D, X to the exponent of small letter d. It is impossible for her to be homozygous dominant simply because the mother at number 4 does not have the dominant allele for SCID, which is going to be normal, result in a person without SCID. So that is all the genotypes of individuals in this family, right? Let's continue. In this example, it says that the pedigree diagram shows the blood groups of individuals of a family. The blood groups are indicated inside the circle or the square. The blood groups of individuals W and X are not included, right? So we've got a female and a male. This female has got blood group O, and the genotype for blood group O is to be small letter I, small letter I. Individual with blood group O married a male who is W. But let's look at the children of this individual and this individual. So they had a son who had blood group A, and a son and a daughter who had blood group B. But since the mother has blood group O, I know that each and every one of these individuals is going to have the recessive allele for blood group O. But since this person is blood group A, it tells me that he must also have the allele for blood group A. So this is going to be the only possible genotype for individual A. The recessive allele has to come from the maternal origin, and this I to the exponent of capital letter A has to come from individual W, right? Now, let's look at this person with blood group B. Again, since this person is the daughter of this person, she must have a recessive allele for blood group O. But since she has blood group B, she must also have the allele for blood group B. Now, this allele for blood group B now can only come from individual W. Since this individual does not have the allele for blood group B, she only has the recessive allele for blood group O. Now, this person W here was able to contribute the dominant allele for blood group A here. He was also able to contribute the dominant allele for blood group B here, which tells me that individual W has got the dominant allele for blood group A, and he also has the dominant allele for blood group B. Therefore, the genotype for individual number W must be I capital letter A, I capital letter B. So therefore, individual W must have blood group AB. Remember, the inheritance of blood group AB in humans is a sign of co-dominance. This is to say that both the alleles are equally dominant. So because they are equally dominant, they are expressed equally in the phenotype. Hence, the phenotype is blood group AB. Right. Now, let's look at individual number X. Individual number X was able to give birth to a daughter who has got blood group O, right? But individual number X married this male who is heterozygous for blood group A. So one of the recessive alleles here will come from this male, and we must also inherit another recessive allele from individual number X. So there are a number of blood groups that are possible for individual number X. First of all, individual number X may have blood group O. If individual number X has blood group O, it is possible for individual number X to contribute one recessive allele and this individual with blood group A to also contribute another recessive allele, resulting in an offspring who has blood group O with the genotype small letter I. But individual number X may also be heterozygous for blood group A. If individual number X is heterozygous for blood group A, it is still possible for individual number X to contribute the recessive allele small letter I to this individual. But again, individual number X may also be heterozygous for blood group B. If this person is heterozygous for blood group B, it is still possible for her to contribute the small letter I to this individual. So the possible genotypes for individual X, there are 3 possible genotypes that will still result in this offspring here who has blood group O, right? And those are all the genotypes involved in this pedigree diagram. Now, this is a challenge I'm going to leave to you. Try to draw this pedigree diagram, and until next time, bye-bye.